So Louis is a Canada Research Chair on Quantum Materials at the Université de Sherbrooke in Canada. He is an experimentalist working on strongly correlated systems, especially on HTC superconductor. Louis has made a significant contribution to the cuprates, especially in the high-field regime. His work has been recognized with several awards, including the Summer Memorial Prize in 2017 and the Heck Kamerlin Honors Prize in 2018. So today, Louis will tell us his recent work on pseudogap matter in whole-doped cuprates. So let's welcome Louis. Louis, please.
Thank you very much. Thank you very much, Louis and Juven and the organizers of this great series. I think it's wonderful to have that, and you've done very well with a fantastic list of speakers throughout the year. So congratulations on organizing that. So today I'll talk about experimental signatures of the pseudogap phase of cuprate superconductors. And I'll be touching on the work of several of my students and postdocs and research professionals at Sherbrooke. So for those who don't know, Sherbrooke is in Quebec. So that's the French part of Canada. It's north of Vermont, if you're in the States. And so I'll go through a number of experimental studies that we've done. And if you have any questions, don't hesitate to stop me. I'd be delighted. I'll go sort of succinctly on different experimental results. And if you want me to dig more and show more, then please ask. So this is the phase diagram, a sketch of the phase diagram of cuprate superconductors. So most of you will be familiar with this temperature doping, hole doping in this case, hole concentration, measured per copper in the copper oxide planes of these materials. So as we go from zero doping to high doping, we go from a Mott insulator, where charge doesn't move, no charge motion, no electrical current flows, to at high doping above 0.3, we have a metal that is more or less like a conventional Fermi liquid. So all the action is really in between these two extremes, and in particular, superconductivity appears. It forms a dome shown by the dashed line here. The maximum value of this dome can be as high as 150 Kelvin or more, so halfway to room temperature in some of these cuprates. But also, so our approach, in fact, our experimental approach for the last several years has been to study what happens if you remove superconductivity. That's why it's a dashed line here. So we apply large magnetic fields to suppress superconductivity to zero and basically measure down as close as we can to the t=0 axis. So our study is to see what happens as we go down in doping from high doping to lower doping. And in particular, two phases have been of interest to us. One of the phases is called CDW's charge density wave. It's indicated here by this dome around 12% doping. We won't talk about that particular phase today. So the other phase that we've been focusing on more recently is the so-called pseudogap phase, PG here. This is an enigmatic phase of matter that is still not clearly identified. It's not clear whether it has some kind of broken symmetry or not. So we're trying to gather robust experimental data to define it. So we're going to study properties around this point, which we call P star. This is the critical doping where the pseudogap phase ends, where this T star line comes to zero. So you can review a lot of what I'll say today in this recent article with Cyril Proust. So main findings, there are five things I'd like to touch on. So one is a drop in carrier density across P star. Another one is a phenomenon that's come to be called Planckian dissipation, associated with T-linear resistivity. Very intriguing, fascinating phenomenon, which recently we've been able to shed light on by doing measurements of something called ADMR, this angle-dependent magnetoresistance. So there's a recent preprint on the archive. I'll talk quite a bit about this. And I'll talk also about thermodynamic evidence of quantum criticality at this point P star, at this critical point P star. And finally, show you a surprising discovery that our group made last year of a large thermal Hall signal, even down into the mod insulators at 0 doping. So we're still trying to understand where that Hall signal comes from. And at the end, if I have time, I'd like to show you data that we haven't shown yet anywhere that reports on observations of most of these features in a new material for us, bismuth 2201. So the work done here is not on bismuth 2201, but now we have several of these studies have now been done in this other cuprate. So it's very interesting to compare results in this material as well as the others. So let me start with this, just a quick overview of the basic properties of the pseudogap phase. So one of the materials we'll focus on is ND-LSCO. Sorry. ND-LSCO is LSCO with some neodymium, and what the neodymium does is lower the TC, in fact. So the TC is relatively low, maximum about 20 Kelvin in this material. Because of that, we don't need such high fields to fully suppress superconductivity. So it's convenient, actually, if you want to study the properties of the normal phase without superconductivity. Here, I show the resistivity at two very close dopings, 24 and 22, and you can see there's a dramatic change as you go from 24 to 22. 24 is characterized by this T-linear resistivity I'll talk about in a little while, which refers to this Planckian dissipation. So that's actually just above the pseudogap critical point, which in this system is 23, 0.23. So P star is 23%. If you go just below that, you see all the properties change, including all the transport properties, and the resistivity in particular goes up quite a bit. But it's a metal to metal transition. Pseudogap phase, even though this looks insulating perhaps to some, in fact, this does go to a finite value when you can verify the Wiedemann-Franz law there, for example, at 100 millikelvin. So this is really a metal. So, but this metal is obviously different from the metal above. And you can define a sort of crossover temperature T star for where the resistivity deviates from linearity. Here you would have about 50 K. So this is this point here. Okay. Now, the nice thing about ND-LSCO is that there's been some beautiful ARPES studies of this material by the group of Johann Chang in Zurich. And he's studied basically all the dopings that we've studied. So from the spectroscopic probe, ARPES, where you see this antinodal pseudogap, which is really the definition of the pseudogap phase, you can see that at 20%, you have this antinodal pseudogap right here at 20%, but it's gone at 24. So this agrees very well with the transports. So we see no sign of pseudogap at 24, and they don't either. And at 20, there is. In fact, you can define the temperature where this antinodal pseudogap closes, say at 20% doping, sorry. And you see that it gives you this square here, which agrees very well with the resistivity. So there's a good match between transport signatures of T star and P star and ARPES. So we know we're looking at the right phase, the pseudogap phase. Okay, the first property I'd like to highlight is a drop in the Hall number. So these are high field measurements of the Hall coefficient. They were first done in Toulouse with Cyril Post on YBCO. These are the blue dots. So I'm plotting the Hall number in units of holes per copper. Okay, and then we repeated this on ND-LSCO, the material I just showed you, measurements in Nijmegen in particular. And very recently, there's been a nice series of measurements on thallium-2201, another single layer cuprate. This is by the group of Tony Carrington and Nigel Hussey, and they've seen also a drop in the Hall number. So what we see is that the drop from 1 plus p to p in the Hall number at p star in both of these, p star being known from separate experiments, is a new signature, is a robust signature of the pseudogap phase. In Taillefer-New 201, it's interesting that there is no other measure of p star. So the question of where p star is in that material is still open. But what I would say from this comparison is that it's very likely that that p star is at 26% or so in this material. Okay, so that's the first signature I wanted to mention. Carrier density goes from 1 plus p to p. So obviously, the question would be, well, what happens is, are we breaking translational symmetry at p star? But there's no clear sign of that in terms of long-range magnetic order, for example. Is it short-range magnetic order? Is it antiferromagnetic correlations? You know, these are the questions that this result raises. If there's no, yes?
Sorry, Louis, can I just ask a quick question?
Yes.
Hi. So thallium 2201, is it not known from the transport from the where the linear resistivity deviates from linearity? Whether there's any such deviation?
Yeah, good question. So the problem is that this is all mixed up with superconductivity in this case, because TC is high, and because it looks like the P star is much more to the right than in YBCO. If you're confined to the overdope region, which we are with Taillefer-New 201, it's actually very, very difficult to get samples below optimal doping. You basically have a TC that rises in tandem with a T star, and they're all sort of mixed together. It's difficult to have you don't have an underdoped, nice underdoped Taillefer-New 201 that shows you a clear signature of T star like you have in YBCO, for example. So resistivity does not allow you at the moment to really say that you're seeing a T star, in fact.
Mm-hmm.
Much of the T star line is below TC, as you approach the critical point, for example. So no, yeah, it's not clear from the resistivity, actually.
Okay, thanks.
Okay, so let's now look at this question of resistivity, and so we're gonna study doping just above P star. So there's no pseudogap, there's no charge order, there's nothing. We're in this region here. It's a region that's often called strange metal because it's not like the Fermi liquid where the resistivity is nice and T squared as you expect. But as you move closer to this point, things change and you go into a regime which you might call non-Fermi liquid or strange metal, or the behavior becomes anomalous, okay? So this is the region that my student, PhD student Annelle Legros studied. She's now a postdoc with Peter Armitage at Johns Hopkins. And she wanted in particular to see whether this T-linear resistivity that's characteristic of, say, LSCO and ND-LSCO, as I just showed, actually is observed in systems with higher TC in other cuprates. So this is a collaboration, again, with Cyril Post, high field measurements in Toulouse, on samples provided by Hélène Raffi and Dorothée Colson in Paris. So this is the phase diagram. So the material she decided to focus on is this double layer cuprate 2212, the most heavily studied cuprate from the perspective of STM and ARPES, for example, but not so much for transport. So she obtained samples that are as highly doped as we could get, which locates us just above all the signatures, all these spectroscopic signatures of the pseudogap phase. So basically it appears there's no pseudogap, you're just above P star. So P star would be around 22%, and we're located at 23% in this case. So she performed a measurement in high field, 55 Tesla, and these dots are provide the temperature dependence of the resistivity in that material. And so it's very linear, down to as low as we could suppress superconductivity. We couldn't go lower than about 17 Kelvin, because then superconductivity was still there. You can compare that.
Just a quick question.
Yeah.
Can I ask a question? Yeah,
Sure, yes.
I was wondering how you know that the high magnetic fields that you apply to those cuprates will not have also an effect on the material and not only suppress superconductivity, but also could create some other artifacts.
Yeah, that's a very good question. It's one of the nice things about the NDLSCO is that you actually see the upturn in resistivity even in zero field. So you can define T star in zero field in that system. And as you apply the field, you can see that all you do is actually just extend to lower temperature the upturn in the resistivity. So we can see very clearly in that case that field doesn't do anything to the pseudogap.
Okay, and then you assume it's the same thing for BI2212?
There it's more difficult. It's more difficult to be sure of that. But by analogy, that's why we compare many different cuprates, to see the similarities. Here we're not actually in the pseudogap phase, so we're actually more interested in this T-linear resistivity, and so in this case, you get a nice linear behavior. And the thing that struck us was the similarity in slope. And with NDLSCO at a similar doping. So we started to ask ourselves, well, what controls that slope? Why is that slope? Why does the slope have the value it has? Right? And this basically led to this whole notion of a Planckian limit to the scattering rate. So basically, you get the T-linear resistivity. You extract the slope A or A1 here. And from there, you try to estimate, in this paper here, this was done in the simplest possible way. We estimate a scattering rate just from the Drude formula. So scattering rate is 1 over tau here. But for this, you need some sort of estimate of the mass and the carrier density. So getting the mass from specific heat, mostly, you arrive at an estimate, the sort of simple-minded estimate of this coefficient alpha, which relates the scattering rate, h bar over tau, to kBt. Okay, and you find quite remarkably that this coefficient alpha is close to 1 in all the cuprates that we looked at. In fact, in all the cuprates for which there is known T-linear resistivity at low temperature. So this is bismuth 2212. I just showed you. The NDLSCO is there. You also saw that. I'll show you later on this bismuth 2201 as well. And LSCO is known from the work of Nigel Hussey. There's electron dope cuprates from the work of Patrick Fournier and Rick Green. And we provide just a comparison with this organic superconductor TTMF, this Beshkar salt. All of these turn out to have this, they're all linear. They have beautifully linear, T-linear behavior, and they have this coefficient that's all around 1. This, of course, was pointed out by Andy McKenzie and colleagues in 2013 for other materials like heavy fermions, and they mentioned the organic and even the pnictides as best as you can estimate. Right? But what we showed in this paper is that this actually applies to cuprates, both hole doped and electron doped. So the question is, what is the physics behind this? It's a fascinating question that remains open, I would say. But now we're able to shed further light on this phenomenon with a measurement called ADMR. So this is the work, this is a project that's done in collaboration with Brad Ramshaw at Cornell. So my postdoc, ex-postdoc, Gaël Grissananche, started this when he was in Sherbrooke, and now is continuing as a postdoc with Brad. So this is really the work of Yawen Fang and Gaël Grissananche together, working in the two groups. So ADMR was pioneered by Nigel Hussey many years ago as a study of the Fermi surface of cuprates. He applied this to strongly overdoped Thallium-201. It's a little bit like a poor man's quantum oscillation, if you like. Quantum oscillation is the frequency give you the size of the Fermi surface. Here, what you have is angular variations in the resistance as you tilt the field away from the c-axis, and you induce orbital motion of electrons around different parts of the Fermi surface. And because the Fermi velocity will change and the shape of the Fermi surface changes, these things affect the resistivity, the c-axis resistivity, and gives you all these wiggles. Okay, so this is a plot of the resistivity as a function of angle. This angle here is the polar angle theta for a given azimuthal angle, and then you can change the azimuthal angle. And on the right here are simulations that reproduce the data extremely well and allow you to pull out what the Fermi surface is. So Nigel was able to show in detail what the Fermi surface topology and shape and geometry of thallium-201 was, and this was confirmed later by ARPES and later still by quantum oscillation. And all this works very well. So we decided to apply this technique of mapping out the Fermi surface to NDLSCO. Okay, so NDLSCO just above P star to start with, and this again is a material that was very carefully measured by ARPES. So its band structure is very well known. It's a single band system, which makes things simpler. At 24%, it's actually gone through its Van Hove point so that its Fermi surface is electron-like centered on gamma, as opposed to hole-like centered on Y, as in thallium-201. The group of Johan Chang also measured the z-axis dispersion. And so in the end, they're able to completely parametrize the band structure of NDLSCO 24% with a set of tight binding parameters given here, including TZ, that gives you the warping, which is responsible for the c-axis resistivity. Okay, so here's one set of data. So there are several like this. This is a plot of rho ZZ, or like rho C, c-axis resistance, as it evolves when you change the angle at a fixed field of 45 Tesla. So these experiments are very, very demanding. They require extreme precision, extremely stable temperature, and that you work in Tallahassee with the hybrid magnet, for which you only have 4 days. So these are sort of miraculous experiments when they work like this. And you can see on the scale here that the variations we're looking at here in this material, in this sample, are very, very small. So you need extremely good signal to noise. And so the different curves correspond to different azimuthal angle. Phi equals 0, 30, 45, 90. And they change. And so all these changes and these wiggles and these maxima and minima and all of this encodes information about the Fermi surface. But in fact, not just the Fermi surface, but the scattering rate as well. It's a combination of VF and tau around the Fermi surface. And so what you need to pull out the information is a simulation, basically a solution of the Chambers formula. So a lot of the exercise is to have an algorithm that can find a solution to all of these curves, given a model for the Fermi surface, which is just a tight binding model with T, T prime, T double prime, TZ are adjustable parameters, and the scattering rate, which has an isotropic and an anisotropic part, which also provides you with these two adjustable parameters. So the algorithm takes all these parameters and finds the solution, which it did here. And as you can see, this is a quantitative thing, right? So quantitatively, it arrives at a solution. And it's able then first to deduce the Fermi surface. So that's the Fermi surface, actually, like in 3 dimensions, that comes out of the simulation. These are cuts in the AB plane at different KZ values. And you can then check how the parameters that ADMR produces out of the fitting compare with the RPES measured value. And the agreement is just spectacular. They're basically perfect. So in other words, the ADMR is able to tell you what the Fermi surface is in detail, even if you didn't have any other information, which was the case for Thallium-2201, back in 2003 as well. So this showed that ADMR has complete control over the Fermi surface, as confirmed by this comparison with RPES. So the next question is, okay, well, what scattering rate was required to arrive at this kind of agreement? And so let's talk about scattering rate, and that's the fascinating aspect. So the scattering rate that we asked the algorithm to use as an isotropic part, so ISO, tau ISO in red, and as an anisotropic part. Okay, and so it requires both, in fact, to fit the data. There's no way you can fit the data with one or the other. So you need both. And the thing that was really fascinating to us is that if you plot the temperature dependence of both components, what you find, to our great surprise, is that the anisotropic scattering is temperature independent. So it's elastic. So it's due to impurities. So it's impurities that produce the strongly anisotropic scattering. But the inelastic scattering, which is responsible for this T-linear dependence of the scattering rate, is isotropic. Okay, so let me repeat that. First result, which is in fact, I believe it's the first time that this is measured in any strange metal with T-linear resistivity. We now have a direct measurement of the scattering rate that is indeed T-linear. Okay, so this was inferred from formulas like the Drude formula. It was sort of assumed that the scattering rate was T-linear, but now we're actually showing that it is indeed. Moreover, what we find is that it's isotropic. So Planckian dissipation is built on a T-linear scattering rate that is isotropic. And quantitatively, the number that comes out of this is in picoseconds, inverse picoseconds here, you get an alpha of 1.4 plus or minus this error bar. So very, very close to 1. Of course, there's nothing sacred about 1, but let's say that's what we call the Planckian limit for now. I mean, it could be pi over 2, there's no theory of this at the moment. So, but it's of that order, it's of order 1. So it's got the right magnitude, it's got the right T dependence, and we're finding out that it has no angular dependence. So you can then take the Fermi surface and the scattering rate that is obtained by fitting the ADMR and show that it gives you quantitative agreement with 3 different transport properties. So rho ZZ, which in fact is fitted in the process, so that's not a surprise. And if you like, this is a constraint. So the data is the line here, and the fitting is giving you these different points at different temperatures. But then you can ask, okay, well, what about the in-plane transport, which a priori the measurement doesn't know anything about, but it's contained. It can be predicted, if you like, from your simulation. If you know the Fermi surface and the scattering rate, you can calculate all transport properties. So you can calculate rho XX, and you find that it agrees very well. Modulo this factor. So this is a different sample with different impurities. So we're finding that to get this agreement, you need 0.8, which is quite possible. You find that the Hall number is working out remarkably well. I should point out that the Hall number of an electron like Fermi surface, you would think is naively as being negative. But in fact, it's not negative for the very, very reason of this anisotropic scattering. And it's measured as 0.45 and here something like 0.38. So extremely good agreement, just straight out of the calculation. So we believe we have an essentially perfect understanding of the Fermi surface and the scattering rate in this system with T-linear resistivity. It's interesting to compare then this thallium-221 that I told you about, for which the Fermi surface is known and the scattering rate. Okay, so we're going to compare these two systems, both of which have been studied by ADMR. And first, it's interesting to compare their resistivity. Okay, so this is the resistivity of ND-LSCO I already showed you. Perfectly linear, but also very large slope. And now I'm plotting here the inelastic part of the resistivity divided by the interlayer separation. So this is inelastic resistivity per copper oxide plane, because there's a very big difference in the separation between planes. If you want to do a quantitative comparison between these two, you should really divide by interlayer separation. So what we find is that thallium-221, this was known, of course, for a long time, is not perfectly T. It's T plus T squared. So it has both a T component and a T squared component, and the T component is plotted as a dashed line. So there's a factor of 10, in fact, in the strength of the T linear resistivity between these two systems. And interestingly, if you ask what the ADMR predicts for the Fermi surface, so the Fermi surface is different. Here we have this electron-like Fermi surface very close to the Van Hove point. Here you have far from the Van Hove point, and you have this hole-like Fermi surface that cuts, for example, the antiferromagnetic zone boundary here. So the Fermi surface is quite different, and as a result, the density of states is quite different. If you just calculate from this Fermi surface, you will find that the density of states of thallium-221 is quite isotropic. It doesn't vary very much, and it's low. Whereas in ND-LSCO, the scattering, the density of states goes to very high values at these points here, because there you have this Van Hove saddle point. Fermi velocity goes to 0 there, so density of states becomes large. And that actually explains, in our opinion, why the scattering rate that you pull out of ADMR is so different. This is the elastic component now, so the temperature independent part. In thallium, it's constant, as is the density of states. Whereas we have to have, the fitting requires a very strong anisotropy of the elastic scattering, which we think is a consequence of the strong angular dependence of the density of states. But that's the impurity scattering. More interesting is to look at the inelastic scattering. Okay, so the inelastic scattering, we're comparing ND-LSCO in violet here, which is constant, isotropic. And now we're plotting this in units, in Planckian units, if you like. Alpha equals 1 would be this green line. We're at 1.4 here with some error bar. And interestingly, the findings for thallium is that, and this was the work of Nigel Hussey in this paper here, is that it's strongly anisotropic. So in particular, it goes to 0 along the nodes and then maximum along the antinodes. So in some sense, it's no surprise that you're going to get a mixture of T and T squared in this system. Whereas here, what we find is that to get a pure T linear behavior, you require the scattering rate to be isotropic. So presumably what happens is that as you evolve in doping and you approach P star, this critical doping, your system is becoming Planckian. It's going from anisotropic scattering, peaked at the antinodes, perhaps from antiferromagnetic fluctuations, and then it's just becoming isotropic and maximally strong at the critical point, giving you this Planckian result. So it's wonderful new information that was pulled out by Yawen and Gael, analyzing this data. Okay, so let's move on to. So yes, I'm just going to say, I'm not going to discuss it here, but I'm quite happy to show you. I mean, of course, it's really interesting to ask, well, what happens if you go inside the pseudogap phase now? You have got this great probe of the Fermi surface. You should be able to determine the Fermi surface in the pseudogap phase, which is, possibly one of the greatest questions we need to answer. And so we do actually find a complete change in the ADMR as we go into the pseudogap phase. So there's definitely a change of Fermi surface. So if you want to talk more about that, then I can show you some slides and go through our model for what we think the Fermi surface of the pseudogap phase is. But let me just say that the most consistent, the model that is most consistent with the data, that is, in fact, the only model we found that is able to explain the ADMR that we observe below P star is a model of small nodal hole Fermi pockets. So you go from this large electron-like Fermi surface above P star to small nodal hole pockets, which would be consistent with this evolution from 1 plus P to P that we see in the carrier, in the Hall number, for example. Okay, so let me now show you very briefly a thermodynamic study of what happens at P star.
May I interrupt, Louis?
Yeah, sure, yes.
Yeah, I think it's worth emphasizing that this angle-dependent MR is really measuring. You mentioned it, you describe it as a poor man's quantum oscillation, and I want to emphasize on the poor part. Okay, because so the contrast is that we're now in the omega c tau much less than 1 limit.
Yes.
So the orbit never encloses the Fermi surface. So one is not getting information directly on the Fermi surface. It's a local probe. You measure the local property of the Fermi at the Fermi surface.
Yeah,
so
in some sense, you might say you're measuring VF and tau locally around the Fermi surface.
Yeah, so I think one is probably sensitive to some kind of curvature of the Fermi. So you're probably seeing some kind of motion around the tip, right? I mean, there's a lot of controversy about the backside of this small pocket. So I think one is not really getting any information on the backside, whether it's there or not.
You're talking about inside the pseudogap phase now.
Yeah, in the pseudo, yeah. If you go below your critical doping, and I think it's worth emphasizing that point. I mean, I think it's a great tool if you have a model of the Fermi surface and you can verify it. But then to turn it backwards, I think it's much more challenging. In other words, from the data, whether you can find a unique.
That's certainly true. That's certainly true. Yeah. Yeah, what's very clear is that the Fermi surface has undergone a major transformation.
Yeah, that is clear.
To then really say, with the same robustness that we're able to say above P star, and above P star is just amazing. You get the Fermi surface that you can then show is exactly what RPES gives you. You might say, well, RPES gives us arcs below P star. How come we know? But I think this is running into the question of what exactly are arcs, at the level of transport and quasi-particles going around and so on.
Exactly, yeah.
Yeah, well, we can talk more at the end if you want about that. Thank you, Patrick. Okay, so specific heat measurements. These were done by Bastien Michon and Clément Giraud, 2 students from France who did a co-supervised PhD. So we've had 4 of these. Anaël, in fact, was such a student, also co-supervised with Dorothée Colson in Paris. So they basically do half their time in Sherbrooke, half their time in France. And these 2 guys did their co-supervised PhD with Grenoble, with Thierry Klein, Christophe Marcenat in Grenoble. So Klein and Marcenat are these real experts on high field measurements of specific heat. So it was wonderful to collaborate with them, and we got samples from these different groups, samples of ND-LSCO, but also europium LSCO. So without going into any of the raw data and explanation and so on, let me just show you the end result. And so there's 2 plots I'd like to show you. So let me start first so this is the electronic specific heat divided by T at 0.5 Kelvin, so basically 0, very low temperature, 0.5 Kelvin, in the absence of superconductivity, as a function of doping all the way to 0.4, so the full range. Now, some of this was already in the literature, so the diamonds actually here, the diamonds represent LSCO. So LSCO was known in the wings, if you like. There's no superconductivity here. You're entering the antiferromagnetic region here. It's going to 0. And there's no superconductivity at 33% either. So this is measurements by Nigel Hussey. So these data are in the literature. You can find them in these papers. The new data are the circles for ND-LSCO and the squares for europium LSCO. And there are, I think, 14 samples that were measured. And first thing to note is that whether it's europium or neodymium, just acts exactly the same. They just interweave one into the other. This is a circle, this is a square, this is a circle, this is a square. It's identical, whether you use one or the other, which is nice and reassuring. But the result you observe was just completely unknown, is this huge peak at P star, at 23%. So that is the thermodynamic signature at very low temperature of the pseudogap critical point. Then you can sit at P star or at different dopings and look at the temperature dependence. And this is what's plotted here. So let's start at 11%. 11% is down here. There's charge order here, by the way, in these systems. That's probably why you have this dip here. You further eat into the density of states to form these charge density wave phases. If you sit at 11, or indeed at 15, 12, or 8, you get a constant C over T versus, this is plotted versus log T. But you just get a constant and low value at, at 3 here in those units. As you approach this peak, you start to get temperature dependence. And at the peak, just above, this is 24%, P star is 23, you get this beautiful T logarithmic dependence of the specific. So C over T goes as minus log T, or goes as log 1 over T. And this is the classic signature of what we call a quantum critical point from studies, decades of prior studies on well-defined antiferromagnetic quantum critical point. So let me mention 2 of these. One of these came from phosphor-doped barium iron arsenide, iron arsenide, this iron nictide. So this iron nictide, this is a phase diagram here. Similar to cuprates, you suppress magnetism as you increase concentration X here. You produce a dome of superconductivity. There is a critical point. At that critical point, you see nice linear resistivity. So a lot of the phenomenology is very similar, in fact. The difference is that you don't have a pseudogap phase. This is all magnetic, and it's the magnetic order that ends here. So in that sense, it's a clearly defined critical point. And if you measure the specific heat, as was done by Tony Carrington and Yuji Matsuda in different ways, actually, either by looking at the jump at TC or quantum oscillations in the mass, you see this divergence of the specific heat, this big peak at the critical point. So that's very similar to what we observed. If you knew nothing else but the measurement I just showed you of specific heat, you'd say, wow, this is a textbook magnetic quantum critical point. Earlier measurements, in fact, yes.
Yeah. So you have emphasized that there's a Van Hove singularity right there, 0.24. In fact, you use that enhanced density of state to explain the
scattering
rate. So can this be a consequence of the Van Hove singularity?
Right. So we have, of course, looked into this very carefully. And you can show by doing calculations that the Van Hove singularity that we know very, very well in neodymium LSCO would give you, I can show you some calculations that would give you something that is broad like this. Mm-hmm. And the reason why it's broad is that the system is not at all 2D, actually. So in a perfectly clean, perfectly 2D metal, you do get this kind of logarithmic divergence just from the band structure. But if you have a TZ, the minute you put a TZ, you actually have a different Van Hove point at different KZs. So this completely washes out the singularity that you get in 2D. And in fact, it gives you a very broad peak.
You make a remark, Louis, in relation to this discussion. And
yes. Hi, Chandra.
Hi, Louis. what's very, very remarkable about this coefficient of the log is intimately related to the coefficient of the linear. If you know one, you automatically know the other quantitatively, not just cuprate shown, but also in the heavy fermions and the antiferromagnets that you showed. And I think that's very significant. If I may be so immodest, I should say that these things were predicted 30.
We're losing you, Chandra. I don't know why.
Because it's immodest.
I've said all I want to say.
Yes, so thank you. So I think bottom line is that this cannot be due to just simply to a band structure.
Well, let me follow up on that. I mean, I think that is based on some band structure calculation, and I mean, I want to believe that. For example, you could have a reduction of the covariance factor, the Z factor, which would affect the Z-axis hopping. You can imagine that the quasi-particle are not, that strong a quasi-particle, and we have evidence for that because they're kind of broad, right? And
yes, except that now with the ADMR, we have exquisite knowledge of all this stuff, of the TZ, of the warping. We can quantitatively calculate what rho C is. And it's not a big anisotropy. It's about 250 anisotropy between in plane and out of plane. It's not 2000. So 250, yeah.
250 is not enough is enough to round up this peak.
Oh yeah, absolutely. I mean, I can show you the calculations later on if you want. The other factor, of course, is the impurity scattering. Impurity scattering, if you put it in units, is 20K. And so this persists down to 0.5K. Impurity scattering is never going to allow you to do that if it comes from a Van Hove singularity.
Mm-hmm.
So these are both things that completely broaden out the feature.
Okay, good.
So this is the heavy fermion case studied by van Nieuwenhuizen, who saw down to like 0.1 Kelvin, saw this beautiful log T behavior of the specific heat. Also a nice T linear resistivity down to very low temperatures. Despite the fact that the residual resistivity at this critical point, because you need gold, you need to dope gold into it, makes it quite a dirty metal actually. And so this kind of level of scattering would completely wash out any Van Hove singularity down to 0.1 Kelvin. It's just not possible that this would be from Van Hove singularity. So that's this thermodynamic signature, which is so reminiscent of the magnetic quantum critical point. And now the last thing I want to mention, just to bring to your attention, is our more recent discovery of a completely unexpected feature of the pseudogap phase, that is the thermal Hall conductivity. So this was also work led by Gael when he was in our group in Sherbrooke, and working on samples provided by different groups. So this was done on a number of different cuprates. So basically, the measurement is thermal Hall conductivity. So it's the thermal analog of the electrical Hall effect. You send a heat current along the x-axis. Yeah? So by heating one end, this would produce a delta Tx, so a gradient along the length. But in the presence of a field along the z direction, you can induce a transverse temperature difference, delta Ty. So the thermal Hall conductivity kappa xy is the ratio of these two gradients, so transverse over longitudinal times this longitudinal conductivity. Okay, so it's a simple measurement. It turns out to be hard, and that's why there's not many groups who do that. You might be 4 or 5 groups in our general field who do this kind of measurement around the world. There's Puan Ong at Princeton and Matsuda and at Kyoto and and Christian Hess in Dresden, Cameron Benya in Paris. So it's the reason is that the delta Ty can be 1,000 times smaller than delta Tx. So you have to have a 1 millikelvin resolution, even at 10 Kelvin, for example, which requires great temperature stability. That's the main challenge. These are small signals, basically. So here's the data that Gael and our team were able to produce. So I'm going to take you through this same phase diagram for ND-LSCO. Also includes europium LSCO and LSCO here. But basically, let's start from the highest doping, which is 24%, just above P star. This is the same sample that gives you this Taillefer-New resistivity. If you measure thermal Hall and electrical Hall on the same sample, you find that they match at low temperature. And that's called the Wiedemann-Franz law. Okay, so that's just a property of electrons, and it's exactly what you expect in a metal. So there's really no surprise here. The surprise comes when you go inside the pseudogap phase. So let's go to 20%, 20% though. You see that the electrical Hall conductivity goes down. This is because of this loss of carrier density that we saw. But it never goes negative. It just goes down and stays positive. What you find, however, is that the thermal Hall conductivity goes deeply negative. So something very, very different is going on here. So and to convince you, yes?
Sorry, just to take you back by 30 seconds, the behavior at 24%, so that is strikingly different from what you yourself measured in YBCO a long time back, where in the Hall channel, the Wiedemann-Franz was strongly violated.
Are you talking about in the superconducting state? Or?
No, in the normal state. So in the Hall channel, kappa xy over T sigma xy and optimally doped YBCO was decreasing as a function of temperature.
Well, we were never able to measure. I'm not sure what work you're referring to, because this is with one arm. I see. Yeah, no, that's fine. I mean, when I say the Wiedemann-Franz law, I really mean the T equals 0 limit. Because of course, you will always violate the Wiedemann-Franz law at finite temperature, because inelastic scattering affects thermal transport more than electrical transport. So that's not a surprise. In fact, you see this a little bit here, right? The fact that the red line is below the blue line is to be expected, because there's two ways to degrade a heat current and only one way to degrade a charge current. So the fact that these are different, that's not a problem. And that's what we saw with Puan Ong at very high temperature in YBCO. But in the low temperature, sorry?
The trend was quite different from what I'm seeing here.
Yeah, this was really properties above this kind of temperature. I need to go back and yeah, maybe it'd be interesting we haven't focused on the high temperature regime so much, but this is really the focus is really at low temperatures. So the striking thing here is the appearance of this negative signal in the thermal channel, and to convince ourselves that this was there and real, we just kept going down and doping. So this I'm showing you 20 here. Then we went to 8 and 6 and finally 0. So this is 8 and 6 in slightly different materials. This is europium LSCO. This is LSCO. But now these systems are almost insulating electrically. That's why sigma xy is very, very close to 0. It's still non-zero. It's positive, but it's very close to 0. Whereas this guy is just still there and very large, and 6% still there and very large. So there's clearly this thermal transport does not come from electrons. It comes from something else. And in fact, you can go all the way to 0. This is La2CO4. It's a Mol insulator, and you still have this large signal. So the question is, what is giving a rise to these to this thermal Hall signal? And this is a field that, roughly speaking, is about 10 years old. I think Patrick has this seminal paper that shows that you can get thermal Hall effect in insulators from magnetism under special conditions. So magnons, for example, and this was shown in 2010 as well, that by the Tokura group, that that you can actually get a thermal Hall signal from magnons. So this raises the whole question of what uncharged neutral particles, excitations, can give rise to a thermal Hall. And the surprise about La2CO4, and I remember talking to Patrick quite a bit about it at the time, is that a priori, it is an antiferromagnet. It has magnons, but it doesn't have the symmetry conditions to allow for a finite kappa xy. And there's this so-called no-go theorem that says that a collinear antiferromagnetic order on a square lattice like this would not normally give you any kappa xy. So it was not magnons, actually. So then the question is, what is it? More exciting, more exotic excitations, or phonons maybe. So we're still in the process of studying that, and Subir has done quite a bit of work with his group on this. There are several papers, and these are two. And one of the results that they sort of got to clarify the question of a thermal Hall signal from magnons was to put some Dzierżyński-Moriya term on a square lattice, calculate the resulting thermal Hall signal, and you can get one, but it's very, very small. See, these units here are in the natural units. The signal is 10 to the minus 4. So you see, we're plotting this in those units here, and the signal we're seeing is of order 1 in these units of kb squared over h bar, whereas the calculation here gives you 10 to the minus 4. So it can't be magnons, even when you allow for the possible spin canting in La2CO4. But what they did show is that you could get a much larger signal from spin-ons, so from more exotic excitations that have a chiral character. So we're pursuing these studies, and we're now measuring lots of different materials. And let me tell you, the second study that I think is shed light on the question is not yet quite published, but it's actually online in Nature Physics. So this is again work by Gael, and here the idea was very simple. We thought, how about if we apply heat current along the c-axis? Because basically, these are highly two-dimensional systems, and all excitations that are associated with electrons or spin are definitely confined in the plane. So they move much better. Magnons and electrons, or any electron or spin-related excitations, you'd expect to move much better in the plane. Whereas phonons can move just as easily along the c-axis. So we thought, okay, well, is there a thermal Hall when you send the heat along c? And in fact, there is. So this shows here, this is work by Christian Hess, just showing that if you measure longitudinal thermal transport, so kappa XX and kappa ZZ in La2CO4, you get essentially isotropic result. So this is AB plane, and this is c-axis. Very, essentially isotropic at the temperature we're interested in, low temperatures. And indeed, in our own measurement, this is what we get. Very similar kind of almost isotropic behavior. And so when you go to, and the magnons are only in plane. So the magnons are actually sort of the in-plane carriers of heat that contribute at much higher temperature, because there's a gap. There's also a magnon gap, which means that they can't be responsible for any heat transport below 20K or so. So we did this measurement, and that's what Gael found. He found essentially isotropic behavior of the thermal Hall effect, whether you send the heat current along A or C. So this immediately pointed to phonons in our minds. And then you can do this as a function of doping, and this is a nice result. I think if you go back to the 24% data above P star, you see that along the C direction, there's absolutely no thermal Hall, which is of course consistent with the fact that we got Wiedemann-Franz law from the electrons in the plane. So that tells you that the phonons are not giving you any thermal Hall outside the pseudogap phase. And so finally, if you go inside slightly at 21%, so you're moving inside here, then whoop, lo and behold, this purely phononic c-axis thermal Hall signal is appearing. So it's a fascinating phenomenon. You know, this is really a signature of crossing P star. And the phonons are becoming chiral. So that's the way we summarize the result. And the question, of course, is why and how and what is giving you that chirality? So I might mention that Chandra has an interesting paper precisely on this question of a particular state that breaks certain symmetries like time reversal and inversion, and coupling two phonons of a particular state like that would give you a phononic thermal Hall signal. So there's this is very interesting new signature of the pseudogap phase. And we're now pursuing this in many different directions. You know, we're looking at electron doped, and we're looking at different Mott insulators as well. So I don't have really the time to go into this, but let me just mention that Marie-Ève Boulanger, my PhD student, has just produced a nice work published in Nature Communication here, where she's compared Le2CO4 with two other Mott insulators that have structural differences, and that the similarity of the findings allow us to rule out various, you know, possible mechanisms, you know, associated with, say, domain boundaries, or spin canting, or apical oxygen, or what have you. No, none of these things make much difference. So it's got to be more intrinsic than that. So if you want, I can show you some more data at the end. Okay, so that basically covers the 5, you know, experimental studies I wanted to mention. And now I don't know if I can go on. I don't even know what time it is. Yeah, it's about an hour now. So let me maybe just briefly just go through these signatures in bismuth-2,201, because I think it's wonderful to see universality in the behavior by looking at very, very different material. So bismuth-2,201, the nice thing, it's a single layer cuprate. The nice thing about it is that it's got this beautiful ARPS study. It's got STM study by Jenny Hoffman as well. And this is beautiful NMR data by Zheng at Okayama, where he's used high fields like 44 Tesla to suppress superconductivity, just like we do, and is able to really clearly pin down T star as a function of lots of doping, and therefore is able to produce a phase diagram where the red dots here are T star measured by night shift. And they agree with ARPS as well. So this is probably the best delineated T star line in terms of spectroscopy that we have. And what you find is that P star is a very high doping here, just before the superconductivity dies. Okay. And from the magnitude of the drop, which is a drop in spin susceptibility, you can relate that to a density of states if you want, but it's really, strictly speaking, spin susceptibility. He sees a drop in the spin susceptibility as you enter the pseudogap phase. So the work that I'd like to just flash really is the work of Maud Lizer, who was a master's student in our group, and Anaël Legros, who I mentioned already, who was a PhD student. And this was just posted recently. So we go through 5 different measurements in this, and the same 2 samples, very close to P star. So this is the same phase diagram I showed you, and the gray lines position the 2 samples that we have. We were not able to get a sample above P star, unfortunately. So these are just below P star. This is a zoom here. P star is at 0.4. This is a very high doping. And we're at 0.39 and 0.36 in terms of relative to that point. So T star values are quite low, you know, at 25 and 50 or so. So first result, resistivity, bismuth-2,201. This was known, of course, for many years, has beautiful linear, T-linear resistivity. And again, you know, it's got this slope that, as best as we can estimate, we don't have ADMR on this, but as best as we can estimate, is consistent with the Planckian limit kind of estimate. We measured the Hall coefficient of our 2 samples, and there's almost a factor 2 drop, even though the change in doping is very, very small. You know, we go from 39 here to 36% doping, and there's a large factor. The dots here are the high field measurements in 66 Tesla to kill superconductivity. The curves here are just low field. So you can take those values here 0.8 and 1.5 and turn them into a whole number. And that's what you get here. So the whole number is now plotted, our 2 points are the red points here. Okay, so we add those to the previous three that I showed you before. So this is becoming more and more universal, if you like. This fact that the whole number draws from 1 plus p to p. Now we only have 2 points. I'm showing for comparison points that were in this same paper where the thallium data was reported. They also did bismuth 2201. So these are their data. It's a slightly different way of doping. So it's not strictly speaking the same kind of material, but roughly speaking, it does show the same kind of trend. So I believe this further confirms this evolution in the whole number and the drop in carrier density. It's interesting to compare this drop in carrier density to the drop in density of states measured by NMR, for example. I think it's the first system where we can do that. In the absence of superconductivity at t equals 0, you're now seeing that as we change doping, both of these things occur, and you can even have some structure here you can look into and so on. So this is a nice new comparison we can make, we couldn't make before.
May I ask a question, Louis?
Yeah.
When a magneto oscillation have been measured and size of the pocket has been determined for a few densities, is there any relationship between the size of the pocket and the Hall number in yttrium, barium, copper oxide?
Right. So so the situation is the following. The only material and doping for which this comparison of Hall number and quantum oscillations was done is in thallium-2201, strongly overdoped outside of the pseudogap phase.
No, pseudogap.
But
yttrium, barium, copper oxide.
So there, the thing is that the quantum oscillations that were seen in YBCO were only seen in the phase of charge order, and that completely changes the Fermi surface. So you go and the Hall effect. So you don't have a positive Hall effect. So if I look at this plot here, this is YBCO. If you go below this point, 0.15, suddenly the Hall effect is no longer positive. It is deeply negative. So you're not even on this plot anymore. And the Fermi surface over this range here from 15 to 8% is a small electron-like pocket. So there's no way you can compare that. It's a different phase to the pseudogap phase. I mean, you're basically, the big holy grail is to measure quantum oscillations in the pure pseudogap phase, of course. That would be amazing. Okay, so I think that's it. I mean, that's just the thermal Hall effect. This was already showed in the Nature paper that we also, again, in this material, again, see this deviation from positive electrical Hall conductivity to deeply negative thermal Hall conductivity. So all the signatures in this bismuth 2201 really reinforce the universal character of what I've been describing before. So let me skip this. This is a logarithmic dependence on of the Seebeck coefficient. This, if you like, well, I mean, I can just say that Seebeck, I haven't talked about Seebeck yet, but the Seebeck has this interesting logarithmic dependence just like the specific heat. And in this case, again, we see a logarithmic behavior in bismuth 2201, just as we do in these other guys, close to the critical point. And in fact, very recent work by Clément on bismuth 2201, this is a preprint that we're about to finish. He's been able to measure specific heat of bismuth 2201 in high fields for the first time, and that's what he gets here. So he gets a logarithmic dependence of specific heat, much like we were seeing for europium LSCO that I showed earlier. So these are two samples with slightly different dopings, but you get close to the critical point, you get this logarithmic behavior again. So that concludes what I wanted to say, and this slide is just to perhaps point out and make some connections to the more general field of quantum materials. I think many of the things that we're interested in cuprates actually connect with work that is being done in other materials. For example, this whole quantum criticality has definite connections with McKnights and heavy fermions, for sure. Although there's a twist, of course. We don't have antiferromagnetic order persisting up to here. You know, it stops there. So a lot of similarities, but a clear difference from no long-range translational symmetry breaking. We have this Planckian dissipation that is being studied in other materials, and in particular, there's work by Pablo Arillo-Herrero at MIT on looking at possible Planckian dissipation in twisted bilayer graphene. I think that's very interesting to compare with. And finally, this kappa XY probe, this sort of probe of chiral neutral excitations, of course, is being used very prominently in spin liquids to try and decide whether whether Majorana fermions have been cited, for example, in ruthenium trichloride. And this whole subject of what gives rise to kappa XY, I think, is an exciting new, very broad frontier for quantum materials. So let me stop here and take any more questions you might have. Thank you.
Thank you, Louis, for a very nice talk. Now, is there any question?
Yeah, if I can, Marco Lin. Hi, Louis.
Hey, Marco. Hi. Hi.
Nice to see you. I have a general question concerning this universality of this behavior around P star, in the sense that I fully agree with you that this divergent specific heat, for instance, cannot be accounted simply and trivially by a Van Hove singularity. So this is not just a density of state effect. But as a matter of fact, it seems to me, if I remember correctly, that most of the time in cuprates, P star is in a close proximity to some Van Hove singularity. Do you agree with this statement? Is it what? So I'm not saying that P star is due to a Van Hove singularity, but as a matter of fact, some kind of general observation is that so almost coincide. Do you agree?
So, well, I mean, there are cases where it's true, and there are cases where it's not. So, bismuth 2201 is definitely a case where the Van Hove singularity is very close. In fact, I think the Van Hove singularity is basically coincident with P star here. They see this from RPES, where they see the Fermi surface. It goes from this very large Fermi surface because it contains 0.4. This is huge value. 0.4 holes in the volume of the Fermi surface seen by RPES. But then if you go slightly above that, for sure, by the time you're at 0.42, the Fermi surface is electron-like. So there it's true. And the LSCO is true. LSCO is true. But otherwise, thallium, very far from Van Hove. YBCO, very far from Van Hove. So, the fact that we see, for example, very similar drops in the Hall coefficient in systems far from Van Hove compared to systems close to Van Hove shows that it's not the Van Hove that's relevant, at least for that property.
So the answer is sometimes yes, sometimes no.
That's right. That's right.
Okay. Thank you.
Louis, you showed the T-log T on bismuth 2201 on neodymium LISCO.
Yeah.
And I noticed that there is a significant difference. Have you checked whether the ratio of the slope in the resistivity of the linear in T, the ratio of the slope of the T log T in the specific heat is more or less mandated?
So this slope here, how does this slope is not very different, right? It's pretty comparable. Of course,
I would say that I see about a 30% difference, and I think there should be a similar difference in the
right, that's very interesting. We can certainly check that. I mean, I showed the slope, right? The slope was here. So this is the slope per copper oxide plane, which presumably is what you want to do. And they're
because both are single layer. Both are single layer. So yeah, I think that should be.
They're both single layer.
Yeah. Less slope. We see a smaller difference.
They might. Yeah. That's something that we can look into. Yeah. I would say first look, the slope in resistivities, the slopes in resistivity are similar, and the slopes in specific heat are similar. But if you want to be more precise, I need to put my ruler on there and just compute the slope.
I did. I mean, linear in T resistivity at a critical point, the T log T specific heat is absolutely sort of zeroth principle many-body physics. And there has to be a relationship between the coefficients.
Right. So Chandra, what do you make of the isotropic T-linear scattering rate that's coming out of the ADM model?
I have to say, Louis, that there was a paper written around 2002 when the first time isotropic scattering rate was measured with angle resolved photoemission, and by Kaminsky and so on. Also, it was seen by the guy, and we immediately said that in that case, sorry, the constant relaxation rate we said was forward scattering from impurities, simply far from the plane in which the conduction electrons are moving, which makes it forward scattering.
Yes.
And yes. I think your experiments with Brad Ramshaw and Gisson Munch illustrate that very, very clearly, because if you have forward scattering, then there will be little angle dependence. Density around the Fermi surface is roughly constant, and there will be sharp in the magnitude of the impurity scattering rate if the density of, because forward scattering, the scattering rate simply depends upon the local density of state.
So thank you, Charles. Yeah, so I know all this is very interesting. Okay.
Yeah, so we have several people raising their hands, so I will call them all on this. Yeah, so first, Ethan, you can ask the question now. Ethan Lake.
Yeah, sorry, it should be unmuted now. Yeah, I was your thermodynamic measurements on LSCO. Do you see that the specific heat scales as a function of doping in the same way that you would expect given the log T as a function of temperature? Like, do you also have a log in this as a function of P?
So you're asking me if there's a log as a function of P. I'm not sure. Are you asking what this dependence is?
Yeah, like if I try to do some kind of like scaling analysis on this data, give
yes, well, these lines are more or less log 1 over P minus P star. These lines here, yes. So this is log. So that's what I can say, is that we didn't try any fancy scaling, but if you ask, what is exactly this functional form, it is a log, a little bit like what is seen here, in the pnictide. In the pnictide, this line here, they do fit their data to this form, which also fits our data.
Yeah. Oh, okay, thank you.
Does that answer your question?
Okay, so the next one is Yanting. So Yanting, please ask the question.
Thank you. I have a quick question about the measurement of z-axis thermal Hall.
Yes.
So rather than sending a current along the z-axis, if we send a current along, say, x-axis and measure the temperature gradient along z, that would give us the same result up to a sign, right?
Okay, say this again. You want to send the current along which direction?
Along either x or y, but measure the temperature gradient along z.
Yes. So Yeah, we haven't done that experiment actually. We haven't measured delta TZ. So that's an experiment we haven't done. It's interesting. So sending current along X, the field along Y, and measuring delta TZ. That's not something we have done. Yeah. You think that would be interesting to do?
Oh, I just thought it should give the same answer if it's like phonon because isotropic. But
Yeah,
if it's
probably
like
would. Yeah.
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 Okay. Thank you.
Yeah, that's interesting. Yeah, maybe something we should try. Thank you.
Okay, so the next one is David. David, you can ask the question.
Sure, thanks. Louis, can you hear me?
Yes, hi, David.
Hi, good to see you. Thanks for the great talk. I have a question about the thermal Hall data. So yeah. I see, most of your measurements are done at, 15 Tesla. And two-part question, one of which is it just signal to noise that limits you to working at such high fields? And number two, if you've done lower fields, can you make any statements about sort of the, H approaches zero limit of kappa XY?
Right. Yes. Yeah, we can do lower fields. Of course, it does become a question of signal to noise eventually. So depending on how big the signal is, you can go to lower field for sure. So in LSCO, in our Nature paper, we have in the supplementary, you see the field dependence that we have. The field dependence extrapolates to 0 at 0 field, and it's slightly sublinear at low temperature. So at high temperature, let me just show you a curve. So for example, LSCO here, this red curve here. So if you do a field dependence around here at 60K or 50K, it's perfectly linear in field. If you go down here, there's some non-linearity. It's sublinear in field. So if you divide by field here, then you would find that the signal decreases for different field, sublinear in field.
How low in field did you guys go to?
I think there's measurements down to 1 Tesla.
Okay, great,
yeah.
Thank you.
It really depends on the magnitude. For example, Mariev's data, which I didn't show, but I can if you wanted. It's not hard. Let me just go down and show it to you. She's comparing 3 cuprates, 3 cuprate mod insulators, so it's sort of nice. Let's see. Where is her? Yeah, here. See? So she's comparing, so La2CO4 was, I showed already. So this is kappa XX, and this is minus kappa XY. So I'm just putting minus just for convenience. I'm flipping the sign of this thing. So then she measured Nd2CO4, it's another mod insulator. But for some reason, this crystal has a much better conduction, phonon conduction. You see, it's 4 times higher than this, 4 or 5 times higher. But also kappa XY is 4 or 5 times higher. Then she measured this material that you know very well, right? Strontium, copper, oxychloride. Very nice, purely tetragonal system. And you get kappa XX, and you get kappa XY. And you see, if you compare the red and the green, this is 6, this is 8, and this is like 200. And there's a factor 10 here. But it scales with kappa XX. And for us, this is an additional reason why we think it's the phonons that carry the Hall effect, because you can make the phonons 10 times more conductive. And sure enough, kappa XY is 10 times bigger. So when you get such large signal, this is becoming quite large, then you can afford to really lower the field. I don't know how low Mariev has tried to go, but if there was a reason to really carefully study the field dependence, this is something she could easily do, actually. So why do you ask about the field dependence?
Oh, I'm just wondering whether one can potentially separate out sort of an anomalous component to this.
I see.
But it sounds like at least currently the data points towards 0 as H approaches 0.
Yeah.
Okay, thanks.
Yep.
Okay, so the next one is Dominic.
Hi, so I wanted to ask about this statement of Planckian dissipation. So you define the effective mass by the specific heat, as you said. But then you told us later that the specific heat is, the C over T is actually temperature dependent.
Yes.
It has this log. So how does that
Exactly.
affect what you want to say about Planckian dissipation?
Well, really, in the end, what it means is that this is way too rough a way of doing things, right? So this goes back to this original paper for Planckian dissipation. This was just our poor man's way of trying to extract the scattering rate, which everybody else used. I mean, Andy Mackenzie used the same formula. So you say, okay, I'm going to pretend that this formula works, and I'm going to find some way of estimating the mass. Now, in the electron doped cuprates, it turns out that there are quantum oscillations at these dopings. And so you have a very well-defined mass that you can actually put in here. So the mass, this is a nice measure of the mass. But if you go to NDLSCO, that's why there's a huge error bar here. As you correctly point out, how can you define a mass from specific heat? So we gave it a huge range. It's roughly in this range. That's why there's a very big error bar on the mass here. But now with this ADMR, that's a beautiful thing. You don't need the mass. You just pull out the scattering rate directly from fitting the Chambers formula. And so the number that we get now is much, much more reliable. It's independent. You don't have to assume the Drude formula. You get that from the tau measurement. ADMR is a measurement of, if you like, omega c tau. So omega c is the Fermi surface part, and tau is the scattering rate, and that's what you pull out.
Well, perhaps I'm a little confused about what is being measured, because
in the ADMR,
we don't really have a theory of this state, right? It's certainly not a Fermi liquid. So what exactly is the scattering rate from a fundamental point of view?
Yeah, well, in some sense what you're saying is that it's very surprising that the semi-classical theory on which the Chambers formula is based, with a well-defined Fermi velocity and a well-defined tau, would work. But certainly from the point of view of explaining, the Fermi surface and all the transport properties, it works perfectly, quantitatively. So there's something that works about this semi-classical approach. And the tau that you pull out within this approach, much more sophisticated than just the Drude formula and some approximate measure of mass, is giving you this alpha. Now, maybe what you're just raising the question is, how can we treat a strange metal with such standard theoretical machinery?
Can I make a comment on that?
Yeah.
I think we have to remember some old history, that we actually don't need well-defined quasi-particle for a Boltzmann equation to work.
Mm-hmm.
An example of that is actually electron-phonon. Electron-phonon interaction is scattering rate is pi kT at high temperature. So we don't have quasi-particle in the Landau sense, but we use Boltzmann equation every day. Mm-hmm. And that was explained by Prangi and Kadanoff, before most people here were born, including you, Louis.
No, I don't think so.
Academically born, anyway.
Yeah.
So turns out you don't need quasi-particle to be defined in the Landau sense. In this lifetime is less than the inverse lifetime is less than the energy.
Right.
As long as the self-energy is frequency dependent and not momentum dependent, then you can derive a Boltzmann equation, and everything works. So I think just linear independence doesn't mean that there's no, maybe this more generalized Landau Fermi liquid.
I mean, maybe I can reinforce this point, because maybe just to say that, I didn't show this, but the electron doped cuprates have a beautiful T-linear resistivity from 40 Kelvin down to 40 millikelvin over 3 decades. And yet you get quantum oscillations from this stuff.
Yeah, they are not
quantum oscillations, people would think quantum oscillations can only exist if you have well-defined quasi-particles, yet this is a beautiful, exactly. So it's a little bit the same thing.
Yeah, it's the same thing. There's no conflict.
Yeah.
People forget this.
Thank you for reminding.
Since Patrick raised this Kadanoff and Prange, comes out of Kadanoff and Prange is that you should not be using a specific heat mass in front of the resistivity. So your values, I mean, there is linear resistivity, but the coefficients will be about a factor of 3.
So the question of which mass to use and define in different properties.
Yeah, that's a good question too. But may I ask another question? So
sure.
In that formula, there's also a density.
Yeah.
Right? N over m times tau. So what n do you use?
So we use n defined from the size of the large surface.
So it's 1 plus x.
Yeah, it's 1 plus p. Yeah. So it's outside.
Linear resistivity is observed below this p star.
Well, not at low temperature. It's observed.
Yes. In LSCO, yes.
No, I would say no.
Yeah, there's this paper by Bobinger, and you can clearly see it down to.
I don't think so, Patrick.
I have some ringing. Sorry. Yeah.
No, I think maybe it depends where you put p star, but if you look at Bobinger data, basically, it's linear at 22. It's close to linear at 17, and then it becomes very nonlinear. At 15, it's got a huge upturn, right? So
so between 0.16 and 0.19, there's a linearity down to the 0.
Yeah, but the thing is, I would say we don't really know where p star is with that kind of precision. RPES tells you that p star is definitely, at 15%, you're definitely in the pseudogap phase from RPES. And for sure, resistivity has a huge upturn there. From RPES, there's no pseudogap at 22. Fine, and resistivity is.
No, but your claim is that from NH to the whole number that is already dropped a lot between 0.16 and 0.19.
Yeah, in LSCO, the whole number study is for some reason much less clear, actually.
Yeah, that's true.
It's much less clear. I don't know what's going on. It's might be worth re-examining, but it's not as clear. Yeah, it's not as clear. So I don't know why that is, but yeah. Other questions? Okay.
Can I ask a question?
Yes.
Yeah, all superconducting materials you considered are actually layered material, quasi 2D. On the other hand, actually, when you compared it with heavy fermion, these are 3D. So I just wonder to which extent actually this dimensionality matters for what you just discovered. And I understand that actually it might be really important to say discriminate between contribution of, say, magnons, which are in planes only, and phonons, which don't care. But from other point of view, does it matter really?
Dimensionality, I think, does matter. It's I didn't emphasize this, but if you look at this table here that I showed, at least for the Planckian stuff, all of these systems are strongly 2D, all of them, including the organic. This is called a quasi 1D system, but actually at low temperature, it's really quasi 2D. So, and those are the ones that give you beautiful T-linear. In the heavy fermions, it's you get a variety of power laws. Actually, you get T-linear in cerium copper 6, which is 3D. I don't know, that's what you find. Yeah. But then if you go to other cerium aluminum 3 under pressure, for example, or other heavy fermions, it's more like 4/3 or 1.5. So these powers actually do change apparently depending on dimensionality. In my knowledge, if you have a 2D system close to a critical point, you always get T-linear. But that's not the case generally for 3D. Sometimes yes, sometimes no.
Okay, thank you.
There is another question from Zhou Wang. So Zhou Wang, you can ask.
Thank you. So I have a quick question. So at the very beginning, you showed 0.22 Liscol data about the resistivity, which shows kinds of insulating behavior.
Yeah.
Do you have an interpretation why it's like that, and then at which point it turned to be metallic?
Yes, yes. So this is really the transition into the pseudogap phase, you know, from above at 24 to just below the critical point at 23. And our interpretation for this rise is the direct consequence of the loss of carrier density. So this is still a metal for sure. And because you lose carriers, you know, if you go from 1 plus P to P at 0.2, you go from, it's a factor 6 change in carrier density. And in fact, this is a factor 6 in the residual resistivity. So it appears that basically this rise is just because you're losing, you know, a large part of your carriers. Of course, in general, when you have a transition like this, you will lose carriers, but you will also lose scattering. So the two can compensate each other. The case of pnictides is quite interesting. There, it's a well-defined state. You go into antiferromagnetism. If you have cobalt doped barium 122, a material that, for example, Fisher at Stanford has studied in great detail, the resistivity goes up as you enter into the antiferromagnetic phase. You know, it goes up. Why? Because the loss of carriers is larger than the reduction in scattering. So that's what we think goes on.
Do you see it goes down again at even lower temperature, or is always?
No, it doesn't go down. In fact, it will curve over a little bit. We have actually done detailed test of the Wiedemann-Franz law. So Wiedemann-Franz law is satisfied here, and it's satisfied here. You know, it's the same. And this thermal conductivity we measured down to 100 millikelvin, so it's basically zero. So it's a metal-to-metal transition with a dramatic drop in conductivity as you go below P star, which we attribute essentially to a drop in carrier density.
But this is mirrored in magnetic field or in zero field?
Actually, it's there in zero field as well. So it turns out that you can look at the thermal conductivity in zero field inside the superconducting state. So you leave the superconductivity there, and you just cross, and you'll see the same kind of huge drop in conductivity in zero field as you do in a field that suppresses superconductivity. And that's another way to answer this question that was raised at the beginning of what is the effect of applying a field to everything you do? Well, in this case, for example, we can see that the field doesn't make much difference. You
know? Okay, thank you very much.
Pleasure.
So the next question is from Lo Li. So Lo Li, please ask.
Hey, Louis, interesting talk.
Hi.
Hi. Yes, I'm wondering, comparing your data with Banier's data in thermal Hall effect, whereas in strontium Thailand, he observed a T-cube dependence. Now in cuprates, if it's frozen, do you expect when you cool really cold, make a very low temperature, do you expect to recover that T-cube dependence?
That's a very, very good question. Let me just go back down here with the data. Marie-Ève, we're starting to move into the regime of lower temperatures, but so far most of our measurements stop at about 3 Kelvin or so. But Marie-Ève was able to go down a little bit lower in one of her, let me just go to her data somewhere here. I hope I have her slide here. Maybe not. I don't have it, sorry. She was able to go down to low temperatures in one of these cuprates. And what you find, if you plot kappa over T cubed, okay, as you go down in temperature, and you compare the way kappa XX behaves, which is just your standard phonon conductivity, and kappa XY, you find that kappa XX just rises down to the lowest temperatures to reach some finite value, extrapolate to some finite value at t equals 0. And that value would be given by the boundary of the sample, boundary limited scattering. So kappa XX over t cubed would be equal to, a third CVL, where L is the sample size. If you look at kappa XY, on the other hand, it rises as you go down, but below about 5 Kelvin, it drops. And even as kappa XY over t cubed, it goes to 0. And that is because, well, what we conclude is that you're losing, if the phonons have to couple to something, right, to become chiral. So kappa XY must be phonons coupling to something, and that coupling is becoming ineffective at the lowest temperatures. That's the way we're thinking. These curves are shown they're shown in her paper. You have the reference at the bottom here. You can see those curves actually if you're interested in the low T regime.
Right,
but we need to do more measurements to really flesh this out.
Okay, another question from Macari.
Hey, Macari, good to see you. Whoops.
Oh.
Have we lost him?
Sorry. I am wondering if you see any effect of superconductivity on thermal Hall effect. So just you can measure it in the superconducting state. And when you cross superconducting boundary, is there any feature in thermal Hall effect?
It's very much depends on how good the sample is. So if you study YBCO, for example, where the mean free path is, the elastic mean free path is very, very long. When you enter the superconducting state and you gap out the inelastic scattering, then you have a huge increase in kappa XY below TC. In the dirtier sample systems like NDLSCO or LSCO, the effect is much less strong. But you may get a little bit of an effect, but it's less strong. I think maybe, I don't know if I can, yeah. I think sometimes you see a little bit of a feature, but it's not a big effect. But of course, we prefer to just eliminate superconductivity completely, not to confuse things.
Yes, simply it may be giving an insight on the chirality of phonons, so in interplay with superconductivity.
Yeah, that's interesting. You might think that, for example, whatever the mechanism for chirality is, it would be killed by superconductivity, perhaps. Maybe it's a way to switch it off.
Yeah, that's a question.
That's interesting. Yeah, that's a very interesting question. I haven't thought about that. Because, the question remains, why are the phonons becoming chiral? And there's various proposals. Lou Lee mentioned this work by Kamran Benya, where in strontium titanate, it appears that it's something to do with structural boundaries, structural domain boundaries. So this is why my student Mariev tested this idea by comparing these systems, because La2CO4 is orthorhombic and it has structural domain boundaries. So we thought, okay, let's study cuprates that are tetragonal without domain boundaries and see what happens. And as you can see, you get the same data. So it's not coming, the phonons are not acquiring chirality by virtue of their coupling to domain boundaries. And you see also that spin canting is irrelevant and apical oxygens don't matter. You get rid of them. And so at the moment, we're more tempted to think in terms of intrinsic coupling to something in the plane, in the copper oxide planes, whether it's maybe spin fluctuations or maybe more exotic excitations of the kind that Subir is studying. Or it's what Chandra is proposing is the state of the pseudogap state itself is breaking a symmetry that allows for the kappa XY phonons to emerge. But this is really something we need to study by looking at other materials.
Very interesting. Thank you so much.
Pleasure.
Is there any question? Okay, if not, let's thank Louis again.
Well, thank you very much.
Yeah, thank you, Louis, for a very nice talk.
Thank you very much for organizing this. It was great. It was a lot of fun. The discussion was good. I love it when you don't stop discussion. Just keep going.
Yeah.
Good practice.
Okay. Yeah. Thanks everyone for coming. So.